Good afternoon, members and guests. Welcome to the South African Institute of Electrical Engineers, Electronics and Software Section webinar. It's the IT Sky Above Us by Dr. Davi de Wet. Now I will hand over to, I'll just want to give some pointers to you, and then we can go ahead. Please note, all attendees are reminded to ensure the volume is turned up on their devices. Ensure you have a stable internet connection. This will ensure streaming and audio will run smoothly. Attendees can ask questions via the question panel located within the GoToWebinar control panel. By default, the control panel is located on your right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel. The SAIEE TV, under the webinar producer name, for example, KZN or SAIEE ENS chapter. Section. This channel is updated regularly, so ensure you check that as often as possible for new uploads. Please check on the link that will appear in the chat box shortly to subscribe to the SAIEE TV channel. It is free of charge. And now I will just hand over to our chairman, Mr. William Stuckey. Thank you, William.
Thank you, Gerda. You can see my brief bio on the screen there. I won't read it to you, but what I will tell you is that at one stage, at one incarnation, I actually sold satellite connectivity, but Dr. Davi de Wet knows much more about it than I do. So I'd like to introduce him. Davi has a PhD in engineering, and he's currently Group CEO of can you go to the next slide, Gerda, please? He's currently Group CEO of QCon, and he's Chief Engineer for TUBI, which is a Southern African support satellite broadband service. And he has 30 years of experience in designing and engineering, development and implementation of wireless, microwave and satellite communication systems projects in Africa. And he's the lead solution architect for QCon and has led the QCon Design for Sales program for more than 20 years. And he's a very well-versed man in the satellite issue. Davi, are you ready to start your presentation?
All good, thank you, William.
Okay, let me hand over to you and make you presenter.
Thank you. Just let me know when you can see the screen.
Yes, we see your screen.
Thank you. We will start shortly. Okay, good day everybody. Thank you for joining. We're going to talk about satellites today. So this is the version of satellite you I think refer to, or most of you would relate to. We all talk about rocket science, or something is not rocket science, but yet sometimes it is rocket science. So this is a launch of AMC-12. It's done in Kazakhstan. By the way, the industry has been really upset with the whole Russia-Ukraine thing, because there were many launches of rockets done in the USSR area. So those are launches that typically I think is an icon of the satellite industry. We're talking about launch heights or weights of about 3,000 tons. The IS-28 launch in 2011 was 3,000 tons. 2016, there was a launch of IS-33E at 6,600 kilometers at 6.6 tons. 2020, the SE-12 became the heaviest, about at 7 tons. So quite a massive weight and all in all science achievement to get that type of weight into space. Rockets is used to be quite expensive. We started in 2000, in the early 2000s. It cost about, give or take, 25,000 per kilogram to actually launch weight into the mass into space. But then things has changed. I want to show you this now, which is just sort of changing the paradigm a little bit. This is a suborbital launch. It is this video is a bit better, so we can have a little bit better. But it's more just music in background. So this launch is actually done by wind electrical power from solar and wind generated electrical power. It is a the spin launch. This one here is a 33-meter diameter that was built at a cost of 38 million, vacuum sealed centrifuge type of launch. It can launch up to a speed of 8,000 kilometers per hour. Weight still about 200 kilogram. So it's quite interesting. That's the launch of the projectile. Very different, as you can see. So this is just a very classical, I think, intro to help you move your paradigm. And this is what I really want to talk about today. I want to take you in some snippets on a journey that is basically starting from the rockets and moving on to this type of technology. And then you will understand why we're so excited. I just want to actually minimize this. Okay, so excited about what's happening in the industry. So I'm just going to close this so I can see the screen. So this is what happened with the weight of rocket launch. You can see how it reduced from the top end, then $26,000 per kilogram, 9,000. Then SpaceX was massive announcement in the industry, sub $1,000 per kilogram, and now spin launch, it's going to go for sub $100 per kilogram. So of course, this is changing everything. The cheaper it gets to get stuff into orbit, the more you can get stuff into orbit. And that's exactly what's going to happen with this type of, let me just, okay, perfect. By the way, William, if anything goes wrong, just chip in and let me know. I can't see myself, so I'm not sure whether the feedback is there. You're very welcome just to intervene.
Everything's hunky-dory at the moment. Thank you, Davy.
Thanks, William. Okay, so you can see what's happened with the launch cost, and this is basically driving a whole new environment into space, which is a massive trend. Yes, I know if you're a classical engineer and you're part of mainstream telecom, you probably ask the question, well, when will fiber really replace satellite? That's the question we get. Or you follow the old myths, you know, satellites is expensive, has a latency problem, and is slow. But it's actually not the reality. The reality of the satellite industry is really, really the opposite. We are expecting massive growth. You can see that average 1,700 satellites will be launched by 2030. So the growth in the satellite industry is phenomenal. And we talk about that, and I want to share a little bit with you. I've opted to bring a bit of snippets to you today, so I don't really have a big story leading on to some conclusion. I set myself in your position and say, okay, if I'm not really living the satellite industry day by day, what are the highlights that I would like to know about satellites? So highlight number one is it's changing. It's changing because it became cheaper to get stuff up there, and as it becomes cheaper, we'll get more stuff up there. So that's the key thing you need to know, and it's really going to change on the ground. Next discussion we need to have a little bit is just to give you an angle about LEOs, MEOs, and GEOs. So when you talk to any satellite engineer, he will throw these jargon words around. It actually means geostationary orbit satellites, medium Earth orbit satellites, and low Earth orbit satellites. So right at the left, at around about 35,000 kilometers away from Earth, you have the geostationary orbit. That means the satellite is standing still relatively to yourself. And this is quite important to understanding the evolution that we're going through. If you have a DSTV dish, or you know somebody there, if you've seen it, you know those dishes stand still. They don't move, or they don't look around on tracking satellites. So it means the satellite stands still relatively with you, and as you move, because the Earth is rotating, and as you move around the axis of the Earth, which is around the Sun, again, that satellite stands still relatively to you. Out of interest, by the way, it's called the Clark band. The guy that actually did the math behind this is Arthur Clark. Back in the 60s, he calculated exactly what would the distance be away from the Earth, where the mass of the satellite and the orbital velocities and the gravitational force all balances out, so the satellite stands still relatively to Earth. Very interesting, very useful. It's also the position where it can shine basically on the full face of the globe. So if you can just imagine yourself a torchlight shining onto the globe, if you geostationary, you can actually cover the Earth from 3 locations only. That's basically 120 degrees around the Earth. Coming closer, we have MEOs, medium Earth orbit satellites, around 10,000 kilometers. And coming even closer, we have low Earth orbited satellites, which is around 1,000 kilometers. There's a lot of discussion. Our friend, Mr. Elon Musk, which is very topical and very active in the media, both in terms of SpaceX. By the way, he was very instrumental in bringing that cost down, as you've seen, but also in launching a LEO constellation. So we'll touch a little bit on what's the benefits and where it fits. So just as a reference, always good to know and get that sort of angle of understanding. Also, if we talk latency later, we're talking speeds, we talk capacity, it all relates to what actually do you see. So in terms of the satellites, if we just give you a snapshot in a different location or a different sort of slide, these would be government, commercial, and communication satellites around the Earth. And you can see basically, although I've talked about specific distances, LEOs and MEOs don't really have an exact band. There's different heights above the Earth that have actually been allocated and actually being used for different purposes. GPS, of course, is a very obvious one for LEO. LEO is a very classical application, a long-standing application is GPS, used by us all. And then going to MEOs, and you can see the geo arc right at the end. That's a very accurate and very precise arc that balances the science about gravitational force and rotational forces and all of that. So that is basically the satellite environment. Right now, there's give or take, I think, about 4,000 satellites generally in orbit, and that's really going to boom and expand. So we'll talk about that a little bit. So just some impact on South Africa and bringing it closer to see what are we talking about this industry. Yes, it's up in the sky, it's far away. It's becoming very, very material. The LEO constellations is going to deliver about 200 terabits of capacity into the market. Now, as a reference, CECOM cable was designed for 12 terabits, of which about 500 gigabits is active. So that is one fiber cable. So the LEO constellations is bringing about, give or take, say, about 20 times, a bit under 20 times of capacity into the environment. So this is the reality, and this is what's going to drive applications, user environments, industry changes, and so forth. Following from this, and this is a not very well-known sort of realization, the expected South African LEO satellite market is going to be a 1 billion rand per year market. Now, and this excludes Starlink. I'll talk a little bit later why it excludes Starlink. Starlink has their own little plan, which is a little bit on hold for South Africa. But what is interesting about satellite, we used to say that it's too small for the big ones and too big for the small ones. What I mean by that is, even though satellite revenue is significant, it doesn't really impact on the proper turnover of Vodacom, MTN, Telkom, the big ones. So the top tier operators in our country and in the South African industry, basically for them it's not quite worth it to promote satellite. And that's really why the general reference architects, engineers, end users, businessmen don't really see satellite as top of mind, because they don't see an MTN advert on satellite. They have seen the Starlink and notes and the Elon Musk, and believe me, that has created some interest. But in general, because it's not promoted by the big telcos and you don't see it in all the adverts, then people start to think, well, you know, it's a dying technology. Well, it's actually not. And that's a big number coming into the satellite industry. And of course, it expects the industry to shake up a little bit. And hence, it's a nice talking to you all and then sharing with you something that's probably going to impact the environment sooner than we think. And the way it's going to impact, there's quite a bit of industry shuffling expected in terms of operators and positioning, because you do need a couple of special environments. I mean, QCon is one of those niche operators. It's what we do. We are a niche operator, so we have sort of muscle this technology, and we are getting ready for that 1 billion year type of industry development. Because you need quite a bit of mixed capabilities. Satellite is one of those classical examples where you have to do large scale on a special basis. So you have to be a large scale factory rollout type of operation, while at the same time it's a fairly high touch specialized technology. So quite an interesting mix of skills and rollout which you need to have. So that's sort of what's coming. I'll check the time there. So by the way, I'm going to leave some questions at the end, so I really want to give us enough time to talk. So let's talk about satellite design and technology elements, and really what is sort of behind it, and what is some of the buzzwords. So number one is latency. You might have heard it. Latency is the time it takes for any data packet transfer a communication link, whether it's a fiber link or a microwave link, or of course a satellite link. Now, generally, if you're a gamer, you know very much about latency, and you're very much worried about latency in 1 millisecond, 2 milliseconds. By the way, just a diversion a little bit. You'd be interesting to know that this Starlink FCC filing was actually not done to give connectivity to the masses in the rural. It was actually done for high-speed point-to-point connectivity. The actual latency in the expected Starlink constellation is going to be faster than the fibers between the major nodes. So if you're trading, if you're a financial trader and you trade between London and New York, you're probably going to prefer a link via Starlink. It's going to give you a lower latency, and the same if you're a gamer. So if you're a gamer and you basically have an offshore server, you're also going to enjoy that. But generally, for geostationary satellites, this is the traditional worry, because satellites are far, 35,000 kilometer, electromagnetic wave travels at a defined speed, so it takes a while, about 120 milliseconds to transverse one leg, so it's 480 milliseconds to go for the 4 legs, because it's from the user to the satellite, to the gateway, back to the satellite, and back to the user. So generally speaking, this is the issue. People will tell you, well, satellites doesn't work because it has this latency problem. Yes, it is true, but yet life has moved on. So if you look at the problem, this is latency in an IP traffic world. So if you transfer it into IP, 64 kilobytes per packet, round trip latency, you make that 480, worst case you make it 650, because you want to take some server delays and maybe some terrestrial delays into account. The maximum throughput then is 0.79 megabits per second on that basis. What is then come along is advanced. We nowadays talking about smart satellite services. Tubi is one of the very first smart satellite services in Africa, and we found some solutions for this. So this is really just changing your paradigm to say, yes, there are some things that as stick, we will have latency. And by the way, there's one of the biggest, I think almost missed expectations, is that the new LEO and MEO satellites, while they will be lower latency, will not necessarily replace the GEOs. We'll talk to you a little bit why. So in terms of latency and IP traffic, it's actually, you can resolve it. We do voice, we do video surveillance, we do real-time traffic, team calls, we do everything over satellite. So it's a little bit something I can ask you today, and you have to move on a little bit in terms of latency is not your biggest issue anymore. To understand satellite design, I choose to do it this way, to actually just communicate it to you. What is the issue around satellite service? Because it's a fairly, it's a niche network. It's a bit of a specialized network. You will see very different satellite services out there, and they all have to resolve lots of factors. They have to resolve a Dyson channel, terrestrial interference, intermod, cross-polarization, all these different elements. Very similar to microwave design, by the way. In one aspect, if you're a microwave engineer, it's an art of engineering, it's a calculation. The only little thing about satellites, it's pretty much still analog, which is one of our challenges, by the way. So if you have a friend that's really into art of engineering or this or that, yeah, the satellite industry needs them. We have an internal academy and growth, whatever, mostly because there's a lot of engineering focus generally onto IP and data, while there are still some fundamental technologies that need RF engineering, satellite networks being one of them. So you do these design because you optimize price, availability, quality of service, performance, and all these variables go into a product. And as an engineering ambassador or somebody that have attended the satellite course, if you do have an in a discussion and somebody complain about, yes, but this service like this, or I had satellite like that, I think the biggest contribution you can do in that discussion is to tell the audience, look, it's very much different. You know, a satellite links from the one vendor for one application is not the same from another vendor for another application. So very much a very highly specialized environment. So it's not quite, you know, normally one see what you see is what you get. So what happens if you now can't see the satellite link? Then it gets to brand experience and reputation. So that's a little bit guidance for those of you that are network architects that have exposure, that needs to maybe integrate satellite in scenario, and you need to work with it, calibrate with it. Yeah, you need to look a little bit for the credibility sort of badge behind the discussion. I think at the end of the day, that's really differentiating satellites and solutions. So I want to talk a little bit about satellite link budget. Satellite link budget is a well-known term in terms of the satellite world, talking about design. So what you do is you calculate the power needed to balance the link. And I'm going to use this to give you just a touch on the life of a satellite engineer. And you want to balance these powers so you get sufficient signal levels, which is interesting, by the way, and which is different by a satellite. You know, if you put up a microwave link, yes, you need to point the antennas and you have to align them and you have to calculate the free space losses and make sure you have enough. But other than that, you don't really care that much about power. You care that it's not load shedding and you care that there is power, but you don't really in a microwave point to more network calculation calculate the power you're drawn from the AC. I'm talking now AC power, input power, not radiation energy. And this is one thing that's different on the satellite. One of the key anchor points about the satellite, they are launched and they launched into an environment up into the sky, and the life cycle is generally 15, getting more now, up until about 20 years of experience. These satellites in the sky, LEOs and MEOs will change a little bit. And the thing that actually dictates that life cycle is the onboard energy. And that's really what you need to work. So there's a lot to do about balancing the power of a satellite design, and hence the need for link budgets. And I'm going to bring quickly for you, just try to make the link for you from balancing the power to actually the cost of the link. So first of all, what is the input? We plug into this calculation, satellite power, user terminal specifications, target service price, interesting enough, percentage uptime, maximum data rate, equipment cost, and a couple of other variables, rain fade, and time of year, and locations, and look angles, and lots of parameters. And that what comes out there is actually, in a little bit simplified way, your product. So a link budget is actually a tool that brings the satellite architecture down into a product space. From out of that, you can say, okay, I get a service for an ATM, normal ATM service. I want 99.995% uptime. I'm going to use a 1.2 meter dish, 3-watt piece of equipment. It's typically what you see on any app, so Standard Bank or FNB ATM. I want to need a max transmit rate of 5 megabits per second using a 5 megahertz carrier. And for 10 gigabytes of data, it's going to cost me 500 Rand per month. So that's one scenario. So to let you understand a little bit of the specifications, so let's say if we want twice the data, right, we need twice the power. And this is now where it gets interesting, because we now can increase that 5 megabits per second transmit link. Which used to have 3-watt transmitter, we can get 10 megabits per second out of it if we increase it to 6 watts. Okay, but now keep in mind, we're busy with a rollout of 1,000 sites, and each of those terminals needs now to increase from 3 watt to 6 watt, and hence that's almost a double in cost. So maybe you don't always want to do that. Maybe you want to keep in mind what is the cost of the terminal, and hence you want to look at another option. So we have another option. We can double the megahertz. If we use twice of the megahertz on the satellite, we also get the power. So if we have a 5 megabits per second link, 5 megabits, 3 watt, uses 5 megahertz, then keeping that 3 watt transmitter, we can get that same 10 megabits per second link by using extra power. In this case, we're going to need 20 megahertz, which is the extra power supplied by the megahertz. So this is an interesting paradigm. It's fairly into the science, and I thought you guys was going to appreciate it a little bit. So this is to tell you that I can get power into a link by using more bandwidth. It makes sense because your mod costs are lower, so your signal to noise are better, so you can actually get a better link transfer. But you have now used double the megahertz, so that link is more expensive. The other thing is also reliability. Reliability needs power, and power is megahertz. So I can change the reliability by changing the megahertz. Same type of equation, same type of relationship. The interesting point we can get to, you can get different services in the market. You can get, if we have a $1,000 per megahertz type of service, you can get a service A and a service B that on face value is both a 5 megabits per second link. They are both shared 1 to 10s, but they are different. The one uses 5 megahertz and the other one uses 2.5 megahertz, and hence the cost difference. So then we can have the same service for half the cost, but 27 times worse in terms of availability. So this is to give you an idea from what happens into space productization, what happens to go from the satellites out there to the actual go-to-market product, and why it is different to actually experience different products from different satellites. So a bit of, I think, snapshots in terms of that. So by the way, you can compile your answers, and we'll take questions, we'll take questions and answers at the end. It's a little bit awkward for me, by the way. I more or less prefer an interactive. Let's go network. So if we moved from satellites, I told you a little bit about the satellites, the TUs, the MEUs, the LEUs. Talked a little bit about the key technology aspect. Now let's talk satellites and networks. Now, step number 1, I want you to move some paradigm shifts. What about a geostationary satellite that's got 1 terabits per second capacity on that satellite? Now, remember, the CCOM cable has got 12 terabits. So this is like a 10th of the CCOM cable on one single satellite. That satellite happens to be Viasat 3, and it's planned for 2023, 24 for no other place than, of course, Africa. So very different. Remember that old myth, you say, well, satellite is slow. Maybe not anymore. Latency, LEO latencies are 25 milliseconds. So, of course, they are a lot lower to Earth, and hence the transmission delays are smaller. And we talk MEUs. A MEU link can have up until 1 gigabits per second capacity for a point-to-point link on a medium Earth orbit satellite. So in that sense, and the capacity coming in. So I want you to actually just with me move a little bit on and just sort of be open for what's coming. So in terms of that, just talking about the projects. So some of the upcoming projects, and ladies and gents, I've touched really just on some of them. Of course, our flagship is Tubi. So Tubi is basically leading this pack of smart satellite services coming out. We've got Starlink. I'm sure you've all learned that. There's a product iSky. We'll talk about a little bit about that. There's OneWeb, Viasat, Lightspeed, Amazon is coming out, SES Mpower, Microsoft Azure. These are just some of them. There's literally, I think we're tracking about 14 or 15 of these large-scale mega projects coming in. Industry very dynamic, very developing, quite at a high rate at the moment. So Tubi is the smart satellite service. So in that sense, it's complementing connectivity. It's a value-added services, and basically with a smart satellite service, you can do things like voice, least cost routing, video surveillance, layer 2, SD-WAN, all those functions in terms of smart satellite services. So completely new paradigm, quite successful in the market, and probably leading in sort of the industry of, let's say, the generation 2 type of solutions, focused on business applications, running on a Ku-band global constellation. So that is the 2B technology. Let's talk HiSky now. Interesting enough, HiSky is a IoT terminal. So we've talked up until now about terabytes and gigabytes and high capacity. The satellite industry is also evolving completely to the opposite side of the spectrum, completely down to kilobits per second. That terminal that you see there, which is a little bit of almost a bit bigger than a, smaller actually than a laptop. It includes the antenna and the transmitter and the buck and the modem. So that's basically an all-inclusive terminal. It's not that new in terms. We've seen beacons like that, and we've seen Inmarsat terminals a little bit. The difference here is HiSky operates on a geostationary satellite, and hence the data cost points are a lot smaller. So IoT very active in terms of vehicle tracking, industry, all the classical examples, applications that we drive. SCADA is a big one, telemetry. So that is the HiSky, and I've included that and started with that because that's really the lower end of the market. There's others as well. There's space and sky coming in. A lot of the MEWs, it's as though they've almost discovered the low orbit environments. It's of course very contentious and very even a lot of debates about the regulatory of the skies and ITU and all of that. So moving from there, Starlink. That is the Starlink constellation grid that's planned. Bottom lower corner, you have the box and the dish. So Starlink is going to be about 1,450 satellites at 550 kilometers, 2825 at 110, and 7,500 at 340. So even there, you can see that Starlink is not going to occupy one specific orbital environment. There's quite a bit of animosity between Starlink changing. They are first. There is a little bit of an opinion they are squatting into on space environments now, and regulatory is probably not that signed off as it should be. But that is the constellation coming, and you can see the number of sites there, satellites, 11,000, 12,000 sites, and hence the large scale coming out, 12,000 sites coming in. On launch, then on top of that you have OneWeb and Kuiper, so that's the launch. So in this case they're going to have 20 gigabytes per second per satellite. That's the capacity that's going to be launched per satellite. Latency between 10, 15 and 100 milliseconds. Interesting how they quote it. It's even though it's a low orbit, but now keeping in mind the satellite is close to you, but now you have to reach ground. So it's not necessarily going up to one satellite and going directly down to the ground station. You might transverse a number of satellites and then go down to ground. You might go down to ground in a neighboring country and then have to come back to fiber. So with fiber, so quite a bit of variable, but generally, we're expecting like about 20, 25 milliseconds. Still very workable, still very practical. And then that's also why they are getting ready for actually high capacity point-to-point links that can transverse the Atlantic and continents and really become a rapid fiber alternative. Part of the FCC filing actually allow that for them. Terminal cost, yes, they've revised this a little bit. Terminal cost is $500 per equipment, $100 per month. I think this is a bit up now. There's a premium service launch. There's a bit of skeptics from the business case. Interesting comment, by the way. This is not the first time this type of constellations was tried. The difference as with this constellation, as well as Kuiper, as well as other ones, the business case is completely different. In this case, it's not a innovation that is funded from an investment perspective and needs to be turned around with a return on investment to be profitable to the investors and to be successful. Both these constellations and others are actually launched, developed, and funded at this point in time purely almost by excess investment funds. So there's no pressure actually on the commercial success, and hence that is why they will be commercially successful, because the time they will have the time necessary to develop the markets. Very much a global positioning, USB-based pricing and billing. They're going to switch on in Mozambique. Mozambique has got a regulatory approval, and Nigeria got a regulatory approval. There's no regulatory approval yet for Starlink in South Africa, and we haven't seen that they make pricing localized. We haven't seen that they actually bring pricing into local currency. You engage with them on a US-based environment. Typically 50 to 150 megabits per second data rate. So that's the Starlink package. OneWeb is the other interesting scenario. OneWeb is a LEO constellation, lower in volumes. It's also resident in South Africa. At the moment, 588 active satellites with 8 gigabytes per second per satellite and 16 user beams. I'll show you guys just now. For the terminal, same type of capacity, and they're going for backhaul. So in terms of the web constellations, let me just put that up for you like that. So those are the terminals that's going to be operating on the OneWeb constellation, and you can see at the right and top is how the actual whole global constellation is provisioned. And the bottom part, the Venetian blights type of patterns. So satellites will transfer over the geostationary areas, or the geographical areas, and will actually form like bands of connectivity as they move across. So very dynamic, very active type of environment. So that is the OneWeb constellation, and it's very much positioned to be a Starlink alternative for business. OneWeb is engaging different with the market. They're engaging with the channel and enabling them and bringing that forth. So we've discussed this. This is just a reminder for you again where the latency spectrum sits for the different constellations. Touching a little bit on Mpower. Ooh, I need to wrap up a little bit. Mpower is a completely other interesting model. It is launched in Q2 as high capacity. There will be a gateway in Gauteng, point-to-point links, and I want to show you this. This is how Mpower is actually going to be integrated. So whereas with the other two, you see actually lowered, smaller terminals, more convenient terminals, here you actually see two satellite dishes operating in synchronized transmission mode and operating to different satellites in a synchronized manner. This type of architecture, a completely different type of solution. These networks are like fiber replacement networks. You are talking about 1 gigabyte per second capacity. Typically, we expect rollouts about 200 megabits or 400 megabits. Applications are really high-end industrial environments, mines, campuses, remote campuses, production sites, oil rigs, of course, maritime, the yachts and the ships are big environments for this type of application. So you can see how these operate. So it's completely different type of technology. So yeah, okay. And closing a little bit, and then we'll go to questions. Microsoft Azure, and this is just to give you an idea from how it's going to change. We're going to see now actually the data centers and Azure going up into the service station, and as a service, Azure is actually providing satellite operate as a service for the infrastructure. So Microsoft is getting into that space. Google is getting into that space in twofold, either to start using the satellites or to give cloud applications for the satellite operators, or to have the data centers at the gateways for the data storage. So Mpower has signed already with Azure. So this is one application, for example, for those dual antennas where they will actually bring 400 megabits per second link at 70 milliseconds to any location. This will be changing the whole data center, cloud, big data industry significantly. So we're going to see actually low latency, high capacity satellite links interconnecting data centers. In terms of the network service space, I wanted to leave you a little bit with a summary of where does this fit it. So if you look at GEW is generally low equipment cost, low service cost, and relatively low data rates, although we're talking 20 megabits and beyond. Then MEW is high equipment cost, medium service and high data rates, and LEOs are medium equipment, high service cost, and medium data rates. It also, of course, means that we always will see these constellations in all of them. It's not that LEOs are replacing GEOs or whatever other combination. It's definitely going to live on to see all the constellations interoperable, and we're probably going to see terminals that can operate on different satellite different satellite constellations at the same time. So you have a terminal. If you're into a LEO coverage area, it will use LEO. If you're not, it will use GEO, and it can actually fill in capacity in between. So, ladies and gents, that summarizes my presentation. So, William, over to you for questions and answers.
Thank you very much, Davi. That was excellent. I've learned a great deal. I have a couple of questions of my own, but before I move on to the questions, I just want to thank Minx, Douglas, and Gerda from the SAIEE staff who helped make this presentation possible, and Peter Tolsma from the from the SAIEE station here, SAIEE Electronics and Software Section, who organised this and got you to give us this talk, Davi. We have one question from Bevan Bates of MicroChoice. He's a multi-choice. He says, what is the satellite industry's plan to secure spectrum as IMT is lobbying for use of all satellite assigned spectrum? All studies show that IMT and satellite comms don't mix in the sense of interference to Earth stations. And we'd like to have a go at that.
Sure, and I think you're mostly referring to C-band. Yes, there's a lot of pressure that C-band be moved across, and I think the answer for satellite is going higher. So we're using KU, KA, and the higher KA bands. So in Africa, we still have a large space of C-band capacities, and that is under pressure. But because we're talking, it's similar to cellular, because of all the high capacity and the beam reuse, even the satellite operators want to do KU and KA. So I think over time they will basically allow C-band, which is the 3.8 gigahertz, to be used by the terrestrial networks.
Yeah, thank you, Davi. I think there's another answer to that as well. You referred during your talk to satellites going to digital. I think the biggest problem about Earth stations being vulnerable to interference is that they are analog. They're primarily analog, not digital. If they were digital and they were using the technologies like OFDM and LT and so on, they would be a great deal less vulnerable to interference. Do you agree, Davi?
Yeah, true. I mean, and also the modulation and those codes will also change, yes.
Okay, what sort of timescale are we looking at for moving to digital, fully digital satellites?
They talk about software-defined satellites, which will come in and beam repositioned, and the first ones has been launched. So I would say to start seeing it more and more, William, probably about the next launches, which is 2024. Into some replacement extents. I know IS-28 is up for replacement yet. So.
Okay, thank you. Do we have any more questions from the floor? If not, I've got two more questions for you, Davi. You mentioned that you would have, it's possible to get lower latency by satellite. This seems a bit counterintuitive. Can you explain that for our audience, please?
Yes, I can, and it is a bit counterintuitive. So the more accurate interpretation is that you can resolve latency constraints. So generally, the belief is, okay, we're now talking about, let's say, the two categories. We're talking geostationary, where the latency is around 650 milliseconds. So there, it's about mitigating the latency. And it's about getting the applications to work, even though there's a latency. So yes, in terms of user communication and just ease of communication, we say, okay, the solution counter latency or sort of take care of that. Of course, MEWs are a lot lower, and the LEO orbit is really not a latency discussion at all anymore. They're around 25 milliseconds. So it is about the advances in the actual satellite modems and satellite technology architectures to compensate and get the acceleration in and get the WAN optimization in, so that the applications is not constrained with the latency. I used to explain this, William, in another forum sometimes. If you sit and watch DSTV and you watch, say, a rugby game, it's not that you're not seeing the try being scored, or you see it a bit later than your friend, or you see the guy being, running like that. So latency, the user disadvantage of latency really sits when the application and the satellite link is not really well integrated. Of course, for video it is, and hence if you have a DSTV channel and you are looking for video, you don't really see the issue of latency because it's a one-way broadcast. It's not really this IP back and forth. So, and that's sort of what we're saying is when we talk satellites and you want to talk latency, let's talk about the end-to-end application, and then we resolve the latency.
Thank you, David. There is one of the answers to that is obviously with geostationary orbit, you've got a long distance of 36,000 k's or so. But for low Earth orbit, you can get better latency than fiber without any clever tricks, simply because the speed of light in free air is 3 times 10 to the 8 meters per second, and in fiber it's only 60% of that. So it's actually faster to go from here to there by a direct connection or a radio connection than it is by a fiber connection. So if your connection of between from base station to satellite to user terminal is not significantly further than the equivalent fiber, you can in fact find it faster. You want to comment there? Yeah, and
that's exactly the reason why Starlink is promoting the high-capacity point-to-point applications with UK to New York and intercontinental for exactly that reason.
Yes. Before we move off the subject of latency, there is another way of dealing with the limitation that you showed in one of your slides of an absolute maximum of what speed you can get, depending on the latency. The speed of your connection is determined by the latency, and that's because of the TCP transmit window. In other words, typically your laptop or whatever is set up to send 5 packets and not send the 6th packet until it gets at least 1 acknowledgement. You can change settings to increase that so that more packets will be sent without the acknowledgement, so that you can in fact increase your effective latency. And that's exactly what you're doing, Tubi is doing, by sending acknowledgements without actually having received the packet yet. Am I correct?
Correct.
Okay, now we have several questions from Wendy Rosenberg from Waxmans. The first one is, what is the controversy about ITU regulation in space? Harvey, do you have an answer to that?
Yeah, it's a tricky one. It is a controversy. It's like ITU has regulated Starlink to some extent, but it's actually because Starlink was regulated by the FCC. And up until now, there's now debate whether the FCC really had the power to launch and allocate or the mandate the global constellations like Starlink and like OneWeb. And that's really the ITU. So, I mean, if China has now a project coming out. India's got a project coming out. Russia's got a project coming out. So how are we going to regulate the LEO orbit? It was different in JEWS. JEWS, was the specific arc around the globe, and every country was allocated a particular slot, and it was very much a global type of discussion. And it's as though the FCC has sort of leapfrogged a little bit over the global discussions and just mandated Starlink, and they just run with it. I hope I answer your question.
Yes, if I can add to that, when you're talking about geostationary orbit, there's only one orbit that the entire world has to share. So satellites are assigned slots at, if I remember correctly, quarter-degree intervals, and that is managed by the ITU. Other satellite orbits are vary wildly, shall we say, as you saw, for example, with Starlinks. But what does happen is that the local regulator, so for example, ICASA in South Africa, has nothing to say whatsoever about a Starlink satellite flying over South Africa and me as a user with a Starlink terminal communicating with that satellite. There is no regulation, and then there's no licensing required. However, if Starlink want to install a ground station so they can improve the connectivity, the speed of and latency of data to me in South Africa, they would then require a license from ICASA. And as Darby said, that's already happened in Nigeria and what was the other one? Ghana.
Mozambique.
Okay. The next question also from Wendy is what is it about a satellite that's analog? Please, you take that one, Darby.
It's actually, at the end of the day, all radio waves are analog. So even if you have a digital radio, so to actually transmit information through space, it's analog. And so the calculations in terms of energy and power and radiation is still analog. Yes, the processing is all digital, and if we talk about software defined and we talk later about digital satellites, then it's about the processing and all of that on top of it. But it's really I'm referring to the actual propagation properties of this case of a satellite, and it's equally applicable to radio waves. All waves are still analog, even light waves,
except when they're photons. Okay,
yeah.
can I give another answer there? Essentially, the modulation of the signal for most satellites, yeah, please put something up there, is analog for most satellites, whereas with digital, it's satellites, it's not. And that's things like OFDM, which is orthogonal frequency division multiplexing, and LTE, which is a long-term evolution, which are technologies which have been, some of which have been used in wireless connectivity. OFDM was what made Wi-Fi so possible. LTE is now what we call 4G. So those are digital transmission, digital modulation on the same analog carrier wave as Darby says. Next question, how big is a nanosatellite?
Shoebox. Nanosatellite is about a shoebox size. They can be as light as 10 kilograms.
So it's about a what size?
A shoebox? Normal, yeah. So
isn't it 100 mil by 100 mil by 100 mil?
Yeah.
It's 4 inches cubed or 100 mil cubed.
Yeah.
Yes. Yeah. Okay. So it's about that big. What needs to be licensed and regulated in country? Does ICASA license the ground station network and spectrum to communicate with the satellite? I think I already answered that question. The ground station needs to be licensed. And there are two ways of the in terms of the spectrum regulations which were introduced in 2012 for calculating the fees. One is on the spectrum being used by the ground station, and another is on the number of base stations. And you can't, or you don't always know how many customers you have, so it's quite hard. So basically, you base it on the spectrum that's being used for the transmission, and all spectrum is based on cost charged. All spectrum is based on what's known as the my goodness, I've forgotten the word. It's a pricing mechanism that takes five characters into account: the frequency being used, the surface area sterilized, the bandwidth being used, whether it's shared or not, and whether it's bidirectional single or not, and in terms of the area, whether it's in a high demand area, which is defined as within any metro or Gauteng, or low demand, which is everywhere else, and low demand costs 10% as the high demand. So that answer the question fully? Administrative pricing determination. Okay. How does ICASA manage interference? I'll answer that one as a previous ICASA councillor. there are essentially, it depends what kind of spectrum we're talking about, and there are two ways a spectrum is licensed. One is point-to-point, and one is point-to-multipoint, and this is excluding satellite, which is slightly different, shall we say. If for point-to-point, it's very simple. You define the endpoints of your beam. You've got from here to there, and provided no one else is using the same frequency at the same endpoints at around about the same angle you are, you can send that can be licensed, and it can be, and there is no interference with anybody else. So if you've got a point from a point-to-point connection from Joburg to Pretoria on 1,000 megahertz, and someone else crosses you on exactly the same frequency with exactly the same modulation and exactly the same height off the ground, there is no interference whatsoever. So point-to-point is a relatively simple case. Point-to-multipoint is where you have, for example, you have a cell tower standing up here, and it's serving cell phones in an area, and that area is the service area, and the charge is in fact not based on the service area but on the sterilized area. In other words, there is an area where you can't reuse that same frequency on a point-to-multipoint basis. In other words, you can't have another cell phone station too close, otherwise they will interfere with each other. So instead of being charged on a factor on the hop length, it's now multiplied by the area. And complicated mathematical modeling computer modeling is carried out to determine whether these are going to interfere with each other. And maybe that's a talk I could give to the SAIEE one day on that subject. So yeah, so ICASA, to answer the question, is an application process for a whole bunch of different kinds of licenses, but the two most important ones are the two that I've spoken of. The third one is satellite, and then there are other things like walkie-talkies and ski boats and whatnot. So it's done by a recording process, a modeling process, and and in some cases there is a publication of it in terms of whether there is any objection to that license being issued. Does that answer the question fully? David, do you want to add anything to that?
I'm good, thanks, Willem.
Okay, dokie. Any more questions from anyone? Well, in that case, I will thank you very much, Dr. David de Wet, for giving us a marvelous presentation. I've learned a great deal, and I'm sure our audience have. In the chat, you will see that there is a link to becoming where you can join the SAIEE, which is the South African Institute of Electrical Engineers. It's not only for heavy current electrical engineers, it's for electronics engineers and 5-volt sparkies, like my ex-wife used to call me when I was a control instrumentation engineer. We have computer engineers and all kinds of things like that. So we have CPD courses for those of you who are professional engineers. One of the extra requirements is that you do carry out some continuing professional development. In fact, that applies to other professions as well. There's a link there. We have a channel on YouTube, and we have a monthly magazine which comes out 10 or 11 times, I forget, a year, which is available on the link that you can see there. And you can see also the link to this thing. This presentation, the recording of this presentation, will be made available on YouTube in a few days. So, Davi, I'd like to thank you very much, and Minx, Douglas, Gerda, and Peter, and everyone else.
Thank you, Willem. Goodbye. Cheers, everybody.
Goodbye.